let's dive into what really into the session. So before that, let's just recap. So in the last session, we introduced the notion of first of all, the notion of a binary operation on a set, and then we defined the notion of a semigroup or semigroup. I'm not sure how it's pronounced, whichever. So whatever. Sometimes I will say semigroup. Sometimes I will say semigroup. Whatever. It means the same thing. So a semigroup is just nothing more than just a pair where S is a non-empty set and star is a binary operation. And the only condition that needs to be satisfied is the associativity. Okay, that's it. Nothing more. Nothing more, nothing less. This is the minimal condition that a set together with a binary operation need to satisfy in order to be classed as a semi-group. So Barry is saying semi-group. Okay, semi-group. Okay, let's maybe we settle for the convention. I will call it semi-group.
I think it's one of those tomato things, British versus American.
Yeah, I'm actually confused because obviously I've been living in the UK for some time, but I'm not British either, and I interact with a lot of colleagues from all over the world. So
it depends on where you're at. Like many parts of the world have more of a old English influence on their speech, and other parts have an American influence.
Yeah. And you will see that in my spelling, with the differences between the Z's and the S's. Sometimes I use Z, sometimes I use S.
Okay, so color with an O-U-R.
And just as a disclaimer, also, you will probably see a lot of typos because I was doing this slide, in particular these slides today. So I'm apologies for that. And now that we have obviously the basic algebraic structure, from now on, our goal is really to see what can we do with it. This is what mathematicians do. They define something. The next step is, what can they construct? What can they, extract? What can they squeeze out of the structure, the given structure? So we'll certainly be doing that today with one notion that I will start with today. And another thing that we want to do is to explore, structural preserving maps, maps that respect the algebraic structure. So these are the key things. Someone is saying there is an audio echo. Jermaine Mark is saying that. Is that maybe you, George, maybe? I'm not sure.
I'm not getting an echo. Are others getting an echo when I speak?
Okay, so it seems particularly to just Mark, because all the rest are saying no echo. So, yeah. Okay. So this is the goal going forward. Now that we have this baseline algebraic structure, is to start to explore some of the behaviors that the certain elements have, and try to do something. Try to get something interesting. Okay. And the first notion is this this is another thing where the pronunciation might be might vary. So I say idempotent. George, how would you pronounce this?
I've gotten in trouble both ways. I've also heard idempotent. But,
okay, idempotent. Okay, idempotent. Yeah.
But I'm not going to claim mine is right.
Okay, so this notion of a idempotent. So given a semigroup, we settled with this semigroups, and given an element A, we define this square, A square to be just nothing more than A star itself. Okay, this is very obvious, and I claim that, given that I don't know you guys, you should be able to generalize this to any n. Okay, so I leave that to you, and this actually will come to play at some in another thing. In fact, in here, as you will see in a minute. Okay, so that's it. So an element is idempotent if if you take it square, actually there's a typo here. This is a square equals a. Okay. There is a typo here. In fact, I will correct it. No, sorry. It says here. I'm mistaking. That's why my view. So the definition of
the first one is just a notation, a squared.
Yeah, notation. Yeah. My thing, because of my screen viewing, I was already saying, have I missed the actual thing? So anyway, yeah. So the first one is obviously this definition that we will be using to define the notion of idempotent. Actually, yeah. So my thing is that you can generalize this to n. So A is idempotent if a square equals a. Okay, that's it. And we denote. Yeah, go ahead.
The generalization works because A commutes with itself. So A times A is A times A no matter what order you do it, and same for A cubed and so on.
That's right. Yeah. So we have a tip again from Barry saying idempotent. So it's like idempotent. Okay, I will start pronouncing it like that. Idempotent. No, okay, so Stefano is saying whether is it abelian? No, he doesn't. George, the comment of George does not imply that the semigroup is abelian. It's just A times A by the definition of the binary operation is the same. It commutes, right?
Yes.
That's what you mean. Yeah.
Sorry if that was confusing, but every element commutes by itself.
With itself, yeah.
You cannot altogether get rid of commutativity. Non-abelian just means that there are some elements which don't commute.
Yeah, correct. Okay. So we'll make another convention. We will call idem of S to be the set of all idempotent elements of the semigroup. Okay. Now, here's a very interesting thing. Obviously, it might be possible that a semigroup does not have an idempotent element. That's the thing. In fact, I challenge you to find one. To scratch your heads to try to find one in the thing at home. And also, it's very very interestingly. Also, you might have a situation where the actual semigroup itself is idempotent. So all the elements are idempotent. I also challenge you to try to construct one. If you cannot, actually ping me on Discord. I'll give you a table that generates an example of a finite semigroup that has this property. And this is actually known. When this happens, the semigroup is known as a band. Okay. And when the semigroup, speaking of now that Stefano is saying about this thing of abelian stuff, if the semigroup is a band and it satisfies this, and if it's abelian, then it's called semilattice. Lattice. Semilattice. Yeah, semilattice. Yeah. So it's a very interesting thing. We might come back to this as we move towards monoids. Let's see what we'll do in the next session. Okay. But now let's just start. Let's take it easy. Okay. So here's the convention. So we'll use this. Now, here's the first challenge. The question is if the set of all idempotent elements of S is a sub-semigroup of this guy. I'll leave this as the first challenge. You don't need to do to think. Some of you might already have a hint about it, but for those of you take it as a home challenge. And another challenge is that whether when we have an element in the an idempotent element, then a to the power of n equals a for all n. Okay, so whether it's idempotent also for any power in a way, So this is very interesting. I think I claim that you should be able to prove this. Okay, whether it's true or not. Try to prove it first. Okay, so now let's look at some examples. These are like what I call boring examples, okay? And I hope I didn't. I'm so terrible with the concrete examples. So I hope I didn't make any silly mistake. So let's take the first example. For example, the integers with the in respect to multiplication. Okay. So the claim is that 1 and 0 are the only idempotent elements, right? So the set is equal to 0, 1. Does anyone disagree? Are we all on the same page? Yes or no? Have I made any mistake? Okay, good. So we all agree. Okay, excellent. And this now let's take the same set, but now let's consider another binary operation. In this case, the addition. Okay. So as you can see, it immediately changes. You know. So the takeaway from this is that you can have the same set, but the behavior will change if you change the binary operation. Okay. So you can see in this case. In the integers, the 0 is only idempotent, right? By definition, right? 0 plus 0 is 0, right? There isn't any other element whose, when you add the element, you get the same element. It's only 0 that has that behavior, correct? So we are on the same page, I assume, right? Yeah, okay. And the same with these guys also, you can see. So now, the question is, if there are examples of a semigroup structure where this the idempotent set is not trivial in the sense that it's not 0, or it's not this boring stuff. Before we start going through hunting for such examples, what do people think? There are or there aren't? Yes, there are. Okay, so that's good. So let's try to hunt some examples. Well, an obvious one is this, the matrix example, So, obviously, trivially, these guys, the identity and the thing are idempotent, right? Because zero matrix times itself is 0, right? The identity times itself is a thing. And also, for non-trivial examples, I claim these guys are idempotent. All you have to do is to take the matrix product. Obviously, this can be generalized not just to any n by n matrix, but also if you wanted to deal with complex matrices. Okay, I won't spend much with the matrix examples. I'll try to skim through them because we will have a whole dedicated sections to do with matrices and these things. So for the time being, I want other examples to take the thing. So you actually you get exposed to other examples. Okay, and as a side note, the eigenvalues of idempotent matrices are either 0 or 1. We'll come back to this in the matrix ring section. At some point that we will cover that. Okay, so let's see. These are actually very interesting examples, especially for those of you who are interested in cryptography. Okay, let's see. So let's see Z3, which is 0, 1, 2. Okay, with the binary operation defined by this table. Okay, I hope I got this table correct. It's actually software generated, so So let's look at this. So 0 times 0 is 0. Okay, so and there's no other looking at this table. The only idempotent element then is 0 in respect to addition in this. Correct? Are we on the same table? I'm sorry, on the same table, on the same page. Yeah, we are. Okay, excellent. So let's go to the next example. Now the same set again, Z3, but in respect to multiplication. Let's see. In this case, we have this, and we have our friend 1. So, are we on the same page again? Yeah. I use Wolfram Alpha actually. There's a thing, a better thing where they generate this. Yeah. Okay. So we are all on the same page. Okay. So far, no luck. Let's go to Z4. Let's increase it. Z4. No luck also. Are we on the same page? Yeah. We are all on the same page. Okay, so nothing changes. So we keep getting trivial stuff. Now, surprise, surprise. Let's go to actually, this is what? Okay, so this is addition. Okay, yeah, this is multiplication. Let's look at this. The multiplication example. No luck either in the multiplication example. And because I am very lazy, I already will save you to say that you take my word for granted, and please correct me if later you verify that I got it wrong. I claim Z5 is also boring. Okay. Okay. So it's boring because we have the same situation. So far, we haven't found any non-trivial semigroup with the non-trivial idempotent elements. Now the surprise. There you go. Let's say Z6. Okay, just please help me on the table, because I obviously I was doing this fast, and let's see. Yeah, do we all agree that the idempotent elements of Z6 under multiplication is 0, 1, 3, 4? Looking at the table, if I got the table correct. Looks good. Okay, so yeah.
Very interesting.
You got something, George?
No, I'm liking this a lot. I'm kind of wondering why, but I won't give the hint.
Yeah. So we are on the same page, at least in respect to this table, okay? So this is the first non-boring example that we found, okay? Now, I'll give you a heads up to say that Z7, Z8, and Z9 are also very boring, okay? So I'm saving you from even checking them, those examples.
A question from Stefano, if you could share the code to make these tables.
Yeah. I will share the thing. Yeah, sure. I'll share that on the thing, on the description later on Discord too. Okay. Now, the question is, this is the question: what makes mod 6 case very special? And that's the first question. The second question is: are there more examples, another mod n for n greater than 6, where we have non-trivial idempotent elements? That's the thing. And I drop a hint here is that this has to do with the prime numbers, but I will give you further hints to see if you can get there. Okay. Okay. So let's see another example. These guys. So Z10. I claim after I share the link for you guys to generate the table. Hopefully you will agree with me that Z10 has the idempotent element 0, 1, 5, 6. Z12 has the idempotent element 0, 1, 4, 6, 9. Z14 has this. Z15 has 0, 1, 6, 10. Okay, so the question now, you start to see a lot of them, but there are obviously some missing, some of them, in between and after are still very, very boring. So the question again is, what do they have in common? What do Z6 and these guys, plus these guys also, these ones also satisfy, they are also non-boring. So they have non-trivial idempotent elements. What do they have in common? So the extra hint I'm giving here is that they break a very interesting property of prime numbers. So I won't say which one. I will let you go and think about it. And if you cannot, nobody can pinpoint it. Maybe George, are you planning to do the study session on next Friday?
Yes, I'll give another hint. Wonder why 4 and 9 don't work.
Mm-hmm. Yeah.
This could be a very interesting stuff.
Yeah. And it's really very important, especially for those of you, I know a lot of you are interested in quantum computation and stuff, but for those of you who are interested in cryptography and these things, these guys, at least let's say classical cryptography, mod n, these guys are the bread and butter of cryptography. So you need to understand, feel very comfortable with these guys, playing around with this stuff. Okay.
This is
yeah. Go ahead, Joe.
This is a really good example of a pattern throughout, where a learning pattern where you look at these examples and counterexamples and try and figure out the pattern for yourself.
Yes, that's right. That's right. This is why I'm saying, one of the reasons also we are covering so little to give you time, the opportunity to be doing this. I'm more interested in you getting the stuff than feeding you with as many things as possible. As you know, I'm not optimizing for speed. I'm optimizing for learning. So yeah. So I really encourage you to go through this. And I will share the link of the Wolfram Alpha that generates the tables, and you can play around with these tables, and maybe even play with the other tables. Mod 1000 or something if it does it. Can you? So someone is asking, can I elaborate the binary operation we are using here? It's multiplication. I can tell you it's multiplication.
It's multiplication mod a number.
N. Yeah. Yeah, it's modular arithmetic. Yes, correct. Yeah.
So if you think of the modular numbers, they wrap around. So you don't have integer multiplication where things can go bigger and bigger without bound. Within the modular numbers, they wrap around no matter what you do, multiplication, addition, whatever, they eventually wrap around because there's only n of them altogether.
Yeah, so I really encourage you to go through this. Okay, so now let's go to homomorphisms. So given two semi groups, S1 star 1. So this is the thing. So star 1 is the first binary operation with the in respect to the first set S1, and S2 star 2. Okay, so a map from what a map is, right? From S1 to S2 is homeomorphism if it satisfies this. Okay, you can see if a map F in this case, F of A star 1 B equals F of A star 2 F of B for all. This is key for all A B in the first one. Okay, in S1. Okay, and here this is the binary operation in the thing. So this side of things is done on the second semigroup. Okay, now let's look at these examples. Let's see. So let's consider the additive group as of reals, and consider the multiplicative group of positive real numbers. Okay, so the question is if this map is a homomorphism. This is the exponential stuff that we learn in the thing in I think it's not in primary school. Where was oh gosh, I even forget where is it school level or something that we learn? I mean, it depends also on the country, right?
Yeah, I mean,
yeah.
I learned logarithms and trig functions in high school, but I don't know for the rest of the world.
Yeah, I think it was a high school for most people. Yeah. So I claim that this is a homomorphism. Okay, you can also verify this later. And a second obvious example, in this case, we are sticking with the real 2x2 real matrices because this is like toy stuff. So you can see now the determinant. You know what the determinant of a matrix is defined like this. The question is whether it's a homomorphism from the set of 2x2, from the semigroup of 2x2 matrices to the additive group R of reals, or is it on the homomorphism only on the thing on this other semigroup? So this is what you need to take the properties of the determinant. Okay, so I'll leave this for you to go again. As I was saying, I don't want to too much on the matrix stuff. We'll come back to this later. All these stuff will come into play when we are dealing with the matrix groups. So that's a homomorphism. Now, as you can see, this notion, obviously, those of you who are coming from advanced background, you already learned these notions, whether you studied, group theory, for instance, or you study ring theory, these notions were already like, but this, you can view this, this notion from, this is the simplest possible way of being exposed to this notion, because of the condition of, because semigroups are very, 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 very simple. This is why I really encourage, especially the newbies, to really, wrap your head around this, because the behavior of these things will change as we dress the algebraic structure with more structure. For example, when we add the condition of we dress the set with the group structure, for instance. All these things really matter. So the question, I'm going backwards actually. And another thing I want to, just as a side note, as a motivation, for those of you, I know some people are coming from cryptography, as the name hints, homomorphic encryption has to do with, homomorphism, okay? In fact, the early homomorphic encryption schemes, like the ones that Rivest and Al-Gamal, forgive for the pronunciation, they were built on groups. And so the notion of homomorphism was, the group homomorphism, okay? And the modern ones, obviously, like, the fully homomorphic encryption over torus, for instance, these things are built on much more richer structure, like rings, for instance, So it's really very, 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 this is the simplest for those of you interested in, these type of things, homomorphic encryption, getting familiar, with the notion of homomorphism at this very simple level. This is actually very, it's encouraging. You are encouraged to go and think about these things before we actually get to more complicated structures. And obviously, this is just a side comment. The question we ask them, obviously, this is classical homomorphic encryption. People are asking, can we run quantum computations homomorphically? For instance,
Just a quick typo note. I think there's only one M in Al-Gamal.
Oh, okay. Yeah. So thank you for correcting me on that. And apologies to Mr. Gamal. Gamal. So I really, for those of you interested in cryptography, the notion of homomorphism, even though this is at this point, because of we are dealing with, the notion of semigroups, is very basic, but nevertheless, you have the opportunity to actually start understanding these things. Okay, so here's a challenge for you. The first challenge is this: assuming that we have S1 star 1, S2 star 2 are semigroups. Okay, so the question is, giving a map that we assume, a map F that we assume is a homomorphism. Okay, the question is whether if A is idempotent in the first semigroup, then the image F of A is also idempotent in the second semigroup. Okay, in other words, does the homomorphism take properties from one semigroup to another? That's essentially what you this thing is going to show you, hint you at. Therefore, the notion of, the reason why we say, this thing is structure preserving stuff. And another thing is whether it's true that the image of F, so the image of F is defined like this, F of A such that, A is in the first semigroup, whether this is a sub-semigroup of the second one, okay? Because the image of F is obviously contained in the second semigroup, okay? So that's challenge number 2. I hope I didn't make any typos. The other challenge I encourage you is this So given three semigroups, S1 star 1, S2 star 2, S3 star 3, and given two maps, F that goes from S1 to S2, and G that goes from S2 to S3, assuming they are a homomorphism, the question is if the composition of these two maps is also a homomorphism. So another thing is, if assuming that F is invertible, okay, is the inverse of F, which goes from S2 to S1, whether this is also a homomorphism. I assume, I claim that you are able to verify, to prove yes or no, to answer to this. It's really important for you to play. I know this is like for a lot of you, for some of you, this is like a toy stuff and these things. But for the rest, is even if you know this stuff, just even if you maybe you look at the book and on group theory or whatever, and you saw that okay, yeah, it must be this. I really encourage you to get your hand with pen and paper and try to prove or disprove these things. And another challenge I have for you is considering these guys, these are just random, like I chose them, Z3 and Z3, Z4, Z6, and so on. Try to construct homomorphisms between them, and see.
I would just have a comment for those like me who know group theory, but not semigroup theory, that it is actually important to verify which properties are still true in semigroups.
Yeah, correct. Actually, you will see this is go ahead, sorry.
You can't take it for granted that something's that's true of groups will be true of semigroups.
Correct. And also this brings me to another thing. These notions of idempotent, you will see something very interesting when we get to group theory in a way. This actually tells you how, even though it's a very simple structure, it's actually very interesting because there are some things that carry over, but there are other things that don't carry over. Okay, so I'll leave it to there. We'll come back to this. And finally, the notion, and this is not the end of homomorphisms and isomorphisms, by the way. Will come in. This is just the beginning of it. As we go through, this will come in over and over again. But for the time being, we say that two semigroups are, S1 star 1, S2 star 2 are isomorphic if there exists an isomorphism between them. So an isomorphism is a homomorphism that is bijective. Okay, so a bijective homomorphism is an isomorphism. So from an algebraic point of view, this essentially means that the two semigroups are indistinguishable. It's just the same thing. They just differ in notation, for instance. So. And here's another challenge. This will be very trivial for a lot of for you. Is this is like if you know how to prove the other one, the other challenge. This is like a challenge. Whether the composition of isomorphism is isomorphisms. This also implies in this case that whether S1 is isomorphic to S2 and S2 is isomorphic to S3, does that imply that S1 is isomorphic to S3? Okay, so that's it. As you can see, it's a very short session. Nevertheless, what I really think is for you to go and play around with this. That's why I took my time to do this table stuff and generate this and just for you to see this thing in play, especially those of you interested in cryptography, to be so you are familiar with these, start getting your head around these guys. Okay. In group theory, actually, we will deal a lot with the thing, especially in the general group theory, because I will avoid to use matrices because we will have a whole section of matrices. So I will try to use a lot of concreteness to be more on these guys. Okay. On these guys, using mod n cases, if you will. that way, for those of you who are interested in cryptography, actually you get a lot out of this, because for the rest, the people are interested in quantum computation and these things, the matrix groups will do for you. The same for those who are interested in machine learning stuff. Okay. That's it. So the slides will be, as you can see, it's the session is short. I think we are finishing 15 minutes before, at least. But again, the slides will be available on the thing on the GitHub thing. The replay will be available on YouTube. Join the Discord. I encourage. Follow us on Twitter and or LinkedIn if you you want to get updated about the latest initiatives and so on. But that's it. I know we haven't covered that much, but from next session onwards, we'll start covering more. Picking up the pace a little bit more. This is just as I was saying when we started. I want to use this as some sort of pre-season stuff, right? Instead of hitting you hard with so many things, we go small step at a time, and I hope it's also useful, and also it takes less of your time, in order for you to kind of have the opportunity to dedicate yourself, maybe 1 or 2 hours to do the self studies and interact with the community, and also help others. So yeah, so that's it. Do I have any question, George, that I missed? I know this is I think from the table. I'll share the link to the table.
I think from what I can see, we've answered all of the questions.
Yeah. One thing I want to comment. So we are here on the semi-groups. I think next session we will spend. I will see what else I can. I want to cover. Obviously, we don't want to spend too much time here, but as we get through monoids and these things, we become very closer to groups anyway. So maybe we'll have another session just on semi-groups, and then have 2 sessions on monoids, and then we finally start on groups. So, but let's see how things go. It's also pretty much dependent on the feedback that I hear from people in terms of the level of difficulty and so on. But so far, I just want to ask. I know we could have just jumped into groups and these things. Do you think this was a useful thing to take? Starting with this a little bit more simpler. Barry's saying if the Psycho group is a group, yeah. If it is a group, then it's a non-abelian group for sure. And I'm at the center of the group.
Does it have a binary operation?
Is one word idempotent? Well, I would like to think so. Stefan, I would like to think I'm idempotent as a yeah. So I hope you enjoy it as things are very easy. Things will start picking up. But my hope is that by starting very simple, as you are feeling more comfortable with stuff, even when we get to difficult stuff, your mind is already, in terms of abstraction, in terms of handling with abstraction, your mind is already wired up. So things will become even easier. Than if we just have started with groups. Honestly.
And now in the early stages, it's a good time to review just the basic set theory stuff, subsets, composition of maps, relations, functions, and so forth, because this is kind of the language that everything else is built on.
Yeah, correct. I think that's one of the reasons that we put on the thing. I think saying like prerequisite, you need set theory, definitely, and it becomes more as we, as we move towards the stuff, the more sophisticated things, as you add, this is the thing that you will see, a lot of you, I know those of you like George, the advanced one, you already seen this is, the interesting thing, you might have like the same set, but as you dress the set with more structure, the behavior becomes completely different. It's amazing. This thing. This is what makes abstract maths so interesting. This type of stuff. So, and as a final comment before I check the chat, and if nobody has any question, maybe we can end here. Please join George's call. I'm pretty sure. Okay, I'm going backwards. Join the session tomorrow. I look forward to the session tomorrow with George. Is there anything you want to comment about the session now that we have like we have some time here?
I just have my fingers crossed that everything doesn't go wrong with the network and my computer and the slides.
Yeah. Well, I'm actually happy that we didn't have any issue today with the networking, because I worked very hard in positioning my mobile network on I tested different positioning and this. I even bought an Ethernet cable, a long one.
Okay.
Yeah, so finger crossed. Now this is the positioning, the right positioning for the router.
Like the old TV set rabbit ears, where you have to hold it just right.
Yeah, correct. In this thing of virtual sessions and so on. So, is there any other question or any other comment that you would like to make? Anybody has any questions or anything about not just today's session? I know this is like very short, but the upcoming stuff.
Positive feedback in the chat.
Okay. Somehow I cannot see all the chat. I can just see the thing is I don't know why.
But Stefano is liking the way these lessons are structured.
Well, thank you so much. This is partly motivated not just by my laziness, obviously, because the last time I only have today, actually, because I was running a little bit late with company stuff. I only had like 1 hour and a half to more or less almost 2 hours to do the slides and so on. But the other thing is, I'm looking at, I learned these things in a different way, with the different professors and these things. So the way I'm trying to do it is the way that I would have loved to, these things were exposed to me. So essentially, that's what I'm trying to do. The way that I would love to, my professors back when I was learning these things, the things were structured, and also based on my experience, teaching other people in the past, this all informed this approach, this small step at a time approach, because what really, as I said, I'm not optimizing for speed and how much amount of things you can digest in short time, is like I'm more saying that you actually get the opportunity to digest the important stuff, that's what really matters. So yeah. So thank you. I'm glad that the way I structured it is very useful, and I structured it obviously also based on the feedback of people. I know some people are not like George, who are coming already from a maths background. Yeah, so hopefully this is like in the middle ground. Mathematicians will probably, especially those who are a little further afield, will be probably frustrated. But yeah. One step at a time, I think, is the right approach in these type of things. Okay, so if nobody has any other comment, maybe we end here. I don't know. Does anyone have any final stuff to say? Next week, okay, yeah. So the next session, I think we'll still have this 2 weekly stuff because of my schedule, and I think it's probably the best also because of the group study session. So. We'll keep this.
As long as we are having the every 2 weeks for the lectures, I can do the study session in the in-between weeks at the same time. Yeah.
It also gives people time for them to go and think about these things, in the spare time. Okay. So the next session will be March the 25th.
Sanjay is asking for if there's any good reference?
Actually, this is very a good question, because I think in the first session I said I'm resistant to give any reference to start with on group theory yet, until I have some sort of thing as we go through. But I can find some, some of the things that I've been looking at, for instance, and send it to you personally, because I haven't decided yet what reference and these things. I need, some. The thing with these topics, if you get exposed in a different authors, start from different they expose it differently, and so we have to find the right based on my understanding of the community. I will pick something that I think is in the middle, in a way.
I'll just mention as an aside that there's a well-known method of teaching in higher math, which is no textbook what at all. It's called the Moore method, and you're just given the axioms, and then you're given guided questions, and you have to work everything out. And that's, if you have the time to learn it that way rather than memorizing a textbook, then you will have a deep understanding.
Yes, correct. And I think this approach, thanks for bringing that up. This is actually very suitable for this 2 weeks gap that we are doing in a way, because hopefully you will have enough time to go and think about this stuff that you go through. So yeah. So Barry's saying, I see the Barry's comment. The Moore method is not for the faint of. Yes, it's true, but I actually prefer it in a way, because this is like learning is actually a part of a self-discovery too. If you already you be tempted, to look at the textbook and the solution is already there. One can easily be lazy and just discard it. But if you really want to be hands-on, this is the approach to go. Yeah. Okay, so someone is asking about.
Yeah, I put a link to the wiki page on the Moore method.
Yeah.
The Moore method does need to be complemented, unless you want to go full bore into pure math. It's best to complement the Moore method with a more exploratory, guided approach as well.
Mm-hmm.
But when you, at some point, you reach the point where it's self-study. Nobody's written the book yet. You're writing the book. So at that point, it helps.
Yeah. Yeah. So that's one of the reasons. Yeah. Sorry. Go ahead, George.
It's the same with programming. You can go all through school looking up the answer on Stack Overflow, but then you get a real job and a problem that hasn't been solved on Stack Overflow. What are you going to do?
Yeah, exactly. So you get stuck, which is why by being used to hands-on exploratory stuff by your own stuff. This is how you learn. This is how you actually by getting your hands dirty. This is the best way. It's true.
I'm going to see if I can find, to use a colloquial term, interlibrary loan of some sources on math learning. I mean, in other words, there's some really good books. There's some really good books, but they are copyright, and so it would be a question of to what extent I could share a PDF that would be fair use.
Mm-hmm, mm-hmm.
But since this is a class,
thank you for doing that.
But since this is a class and we're all in this to learn, this isn't a for-profit making enterprise, unless Bambodi is getting rich off this. It's legitimate to use materials.
Yeah, it should be fine. I'm pretty sure. I'm in the same mind as you. Yeah. So if you have it, it should be fine. Especially sharing it within the Discord and the communities thing circle.
Right.
I don't think it's a problem. Yeah.
And it's also a lot of these books are over 50 years old, and it's really, somebody's grandkid might lose a penny in royalties. I don't think it is a great moral issue as opposed to a very recent book.
Yeah, that's right. That's right. So yeah, so thank you. If you find anything, you are most welcome to share. And one thing I want to add about the Discord, I recently added. I think first of all the chat about group theory. So if you want to chat about the current thing, I encourage you to, if it's test. Anything to do with the group, this course, to do it on the thing on the group theory section as opposed to the topology one. And also, someone was asking some questions about how to get started and these things. So this motivated me to create something called "How to Get Started" with a link to post for people, because I noticed we are getting more new people coming in, and we already had like two courses that in the past, so they don't know where to start. So hopefully that will provide some sort of a guidance for new community members. Yeah. Okay. Well, if there is no more any questions, George, if you don't have anything else to add in respect to next week's study session and also your talk, maybe we can end here.
Yes, I think this has gone very well, and I hope it went well for everyone in the audience.
Okay. Thank you for your assistant, George, and thank you everyone for showing up, and for those on YouTube, thank you for watching. I hope you go through the stuff. It's the step by step. We will eventually get to the advanced, complicated stuff, but to get there, you have to go through a lot of boring stuff. So yeah, so I'll see you in the next session. Thank you again, George, and have a good weekend. I look forward to attending your talk tomorrow. And please share the link to you were saying the pre-invitations for the Zoom. Yeah.
Yes, I put that in the chat, but I can put it on the Discord as well.
Yeah, Discord will be 10 because it's permanent there. I mean, the thing is easier to find for me. Yeah. Okay, so thank you so much again, George, and I look forward to seeing you on the thing tomorrow. And to everyone else, I'll see you in 2 weeks. Bye for now.
Okay, bye.